Okay, hey, welcome back. This is Math 1610 review for the test 4, and or is this test 5? I think it's test 4. Oh, yeah, it is test 4. Okay. Right, so we want to go through and just take a look at the types of problems that I'll be putting on the test. This will be one of our written tests. Not in WebAssign. So anyways, 5.1, we're looking at problems similar to 11 to 35 odd. So you will be required to show work on these. X to the 3 halves plus 2x plus 1 dx. So in 5.1, we just learned the integral is basically an antiderivative, and then we gave you a bunch of rules associated with that. So the power rule is the main rule, and we could apply that here. X to the 3 halves plus 1 is the same as 3 halves plus 2 halves, which is 5 halves, divided by 5 halves, same as multiplying by 2/5. And then plus 2 times x squared times 1/2, or over 2 if you'd rather, plus the integral of 1 is just x, and then plus c. Okay. Clean it up a little. Okay, so we should be old hats at doing that kind of work. Let's look at another one. So a lot of these are just kind of rewriting them so you can apply the power rule. This one is definitely an example of that. So it looks like it's something complicated, especially now that we've done all these weirder integrals like inverse hyperbolics and stuff. It's like, oh, I don't know what I'm doing, but no, it's a simple integral. On the test, I don't like mix them all up and randomly order them or anything like that. They're kind of in order as you would have seen them in the book. Anyways, we can butterfly this guy, x all over, square root of x, same as x to the 1/2, and then plus 6 all over x to the 1/2 dx. Then we can rewrite those guys, subtract exponents, you get x to the 1/2, plus 6x to the now negative 1/2, and then we can just do power rules. So this will be x to the 1/2 plus 1 is x to the 1/2 plus 2 halves, which is 3 halves, and then times 2/3, plus 6x to the negative 1/2 plus 1 is 1/2, and then times 2, and then plus c, and then clean it up a bit for your final answer. 2/3 x to the 3 halves plus 12 x to the 1/2, and then plus your integration constant. Okay, and a lot of this just comes down to practice. I've been giving these problems numbers. They're actually just call them examples because these aren't the same as what's in the book. Sorry. These numbers are correct though. So 11 to 35 in the 7th edition Calculus Early Transcendental by Larson and Edwards. Okay, so example, let's see what we got now. A trig problem, 5 cosine x plus 4 sine x dx. And what do we have here? So the integral of 5, then the integral of cosine is just sine x, plus 4 times the integral of sine is negative cosine x. Be a little careful with the integrals. Okay, so it's going to end up getting us 5 sine x minus 4 cosine x. Let's see. So 2 sine x minus 5e to the x dx. Okay, so the integral of sine is negative cosine again, so we have 2 times negative cosine x minus 5. Integral of e to the x, just e to the x right back. Go ahead and clean those up. Negative 2 cosine x minus 5 e to the x plus c. Okay. Here's a curveball. I think I put this on the test last year. Tan squared y plus 1 dy. So there are certain trig identities I expect you all to know. For example, cosine squared theta plus sine squared theta equals 1, you should have that one memorized. Okay? And then from there, you can get these other formulas by dividing out by either cosine squared or sine squared. If you divide out by sine squared, you're going to get 1 plus, if you divide out by cosine squared, you get 1 plus tan squared theta equals secant squared theta. If you divide out then by sine squared, you're going to get cotan squared theta plus 1 equals cosecant squared theta. Okay, but in this case, we only need the second identity here. And that'll allow us to rewrite this integral in a form that is integrable to us. So we're using a y. I just not used a theta, sorry. So secant squared y dy. And then you could just integrate that because you know the derivative of tan is secant squared. So the integral of secant squared must give you tan. Okay. Then don't forget your plus c. Okay, so simple ones like that. 5.2 worked us. We started working with this idea that, okay, the integral is basically an antiderivative, but it has a geometric interpretation as well. In fact, you could think of the integral, in particular the definite integral, as just a measure of area underneath a particular curve. So 5.2, I expect us to kind of be able to do just problems like 29 to 33. So I won't expect you to have all those sum formulas memorized or anything like that. I just want you to be able to do some simple approximations using either the right endpoints or the left endpoints. Okay? So in the first problem, I just want you to use the right endpoints to approximate the area underneath the given curve in the given region. Okay, so for example, f of x equals 9 minus x on the interval from 2 to 4 using 6 rectangles. Okay, so we need to kind of figure out our widths of our rectangles, which are always called change in x, which will always be b minus a over n, where n is equal to the number of rectangles. Okay, so in our case, it's 4 minus 2 all over 6. So we get 2 over 6, which is the same as 1/3. I like to draw a picture of at least the x-axis that I'm integrating over. So I'm going from 2 to 4, and I'm going by 1/3. So 2 is the same as 6/3. So this will be 7/3, 8/3, 9/3, 10/3, 11/3, and then 12/3. And hopefully that's 6 rectangles. 1, 2, 3, 4, 5. Yeah, that worked. Okay. So this is 6/3, 7/3, 8/3, 9/3, which of course is 3, 10/3, 11/3, and then 12/3, which of course is 4. Okay. Okay. So the right endpoints means we're using these guys when we approximate our area. And area is always just the sum of the rectangles. So the area will be approximately f of 7/3 times change in x, which in our case is 1/3, plus f of 8/3 times 1/3, plus f of 9/3, which is 3, times 1/3, plus f of 10/3 times 1/3, plus f of 11/3 times 1/3, plus f of 4 times 1/3. And of course we could factor out the 1/3. F of 7/3, that means just put in 7/3 for x. Okay, so you get 9 minus 7/3. And we could find the common denominator right off the bat if you wanted to. So, 27/3 minus 7/3. And then plus 27/3 minus 8/3, and then plus 27/3 minus 9/3, plus 27/3 minus 10/3. Get myself some more room. plus 27 thirds minus 11 thirds plus 27 thirds minus 12 thirds. Of course, I've set it up so I could do it all in my head, but you probably want to use a calculator. At the end, you get 35 thirds, which is approximately 11.67. Okay. Okay, so that's the right endpoints. I'll probably also have you do a left endpoint version of this game. Use left endpoints now to approximate the area. And let's look at this example. This example a little more complicated, right? Don't want to make it too easy. So f of x is x squared, or actually 2x squared minus x minus 1 on the interval from 2 to 5, and we want 6 rectangles. Okay. So, you know, our change in x, get that first. 5 minus 2 all over 6, which again is 3 over 6, which again is, well, I guess not again, but that's 1/2. The last time it was 2 over 6 for 1/3. Okay, so I like to do a little number line graph. So 2, which is the same as 4 halves, and then 5 halves, and then 6 halves. I'm just moving by 1/2 every time. 7 halves. I'll have to go all the way up to 10 halves. 8 halves, 9 halves, and then 5, which is, of course, 10 halves. Okay. Okay. So using the left endpoints, that means I'm using these numbers now. And I just go and get my area then. So it's going to be, if you factor out the 1/2, you'll have 1/2 times f of 2 plus f of 5 halves plus f of 6 halves plus etc. Okay. In other words, f of 2 is 2 times 2 squared minus 2 minus 1 plus 2 times 5 halves squared minus 5 halves minus 1, sort of a calculator nightmare, plus 2 times 6 halves squared minus 6 halves minus 1, plus 2 times 7 halves squared minus 7 halves minus 1, plus 2 times 8 halves squared minus 8 halves minus 1, plus finally 2 times 5 squared. Oh, whoops, there's still that one, the 9. I forgot the 9. Bloody 9 halves squared minus 9 halves minus 1, plus 2 times 5 squared minus 5 minus 1. That'd be that. Let's make sure I got them all. So there's 1, 2, 3, 4, 5. Looks like I have too many. What did I do? Oh, you don't include the last one. Sorry. So there it is. And then 6. Okay. Then put that in your calculator, and a half hour later, you should get 55 is your answer. Okay. Okay. Let's then move on to 5.4. Let's skip 5.3. 5.3 is just the connecting the area problem and the antiderivative problem. In particular, you get the fundamental theorem of calculus, which we then use in 5.4 to evaluate definite integrals. Okay, so 5.4, we have 9 to 33, problems like 9 to 33 odd. So mainly the bulk of test 4 is integrals. Okay, there's these two parts where we maybe have to do some approximations connecting the antiderivative to area, but then we're just going to jump right back into more integration. Okay, so let's take a look. So example, we have 2x minus 1 dx going from negative 1 to 0. So negative 1 to 0. And so we integrate this guy at 2x squared over 2, which is just x squared, minus x. And then I have some evaluation. Okay, so first plug in 0. You'll get 0 minus 0, which is 0, and then minus, plug in negative 1. Negative 1 squared is 1, minus negative 1. So that's going to be negative 1 plus 1, which will be negative 2. and just a whole bunch of these. Okay, so let's look at an example. And the integral from 1 to 2 of 3 all over x squared minus 1 dx. Okay, I'm going to find its antiderivative. So this is 3x to the negative 2 minus 1 dx. And so I'll have 3x to the negative 1. Negative 2 plus 1 is negative 1 divided by negative 1, which is the same as multiplying by negative 1. And then minus x, I have to evaluate once I clean it up. So I have negative 3 over x minus x, evaluated from 1 to 2. And I just plug in the limits there. So negative 3 over 2 minus 2 minus negative 3 over 1 minus 1. So I have negative 3 halves minus 2 minus negative 4, which will be plus 4. It'll be negative 3 halves plus 2, and then that's negative 3 halves plus 4 halves, which is just 1 half. Okay. Example. So here we have the integral from 1 to 4 of u minus 2 over the square root of u du. Okay, I'm going to butterfly it. So I'll have u over square root of u, which will end up being u to the 1/2, minus 2 all over square root of u. Okay, let's clean it up, right? So it's u to the 1/2 minus 2u to the negative 1/2 du. And then we could do power rules to integrate those. So have u to the 3 halves times 2/3. 1/2 plus 1 is 3 halves. Minus 2u now to the 1/2. Negative 1/2 plus 1 is 1/2. Times the reciprocal of 1/2, which is 2. I have to evaluate this from 1 to 4. So I have 2/3 times 4 to the 3 halves minus 4 times 4 to the 1/2 minus 2/3. 1 to any power is just 1, so I need not worry about that part of it. And then minus 4 times 1 to the 1/2, and again, 1 to any power is just 1. Okay, so what do we have here? I have 2/3, 4 to the 3 halves. So the square root of 4 is 2, and then 2 cubed is 8. Times 8. Minus 4 times 4 to the 1/2 is 2. And then minus 2/3 minus 12/3. Common denominator there. So we get 16/3 minus 8 minus, what is that? 2/3 minus 12/3 is minus 10/3 times a negative will be plus 10/3. And then combining the 10/3 and the 16/3 is 26/3 minus the 8/3. Minus the 8, sorry, the 8 is negative 24/3. Subtract, you get 2/3. Okay. Okay, so it's like 1/2 calculus, 1/2 arithmetic. Let's look at another example. This guy has an absolute value in it. So from 0 to 5, the absolute value of 2x minus 5 dx. So remind ourselves, what is the absolute value of 2x minus 5? That's going to be negative 2x minus 5 if 2x minus 5 is less than 0, which is the same thing as saying if 2x is less than 5, which is the same as saying is x less than 5 halves. And then it's just positive 2x minus 5 if x is greater than or equal to 5 halves. Okay, so this basically means we need to split up our integral to handle the two pieces of that function. So first we go from 0 to 5 halves of the negative 2x. Now plus 5, I just distributed the negative into there, okay, dx. And then plus the integral from 5 halves to 5 of positive 2x minus 5 dx. Okay. Then we're going to get the antiderivatives here. Negative 2x squared over 2 is just negative x squared plus 5x. Evaluate from 0 to 5 halves. And then plus the other guy, 2x squared over 2 is x squared minus 5x. And we evaluate from 5 halves to 5. Okay. And then we have to do some substitutions. So I have negative 25 fourths plus 25 halves. Okay, that's the first part. And then minus, plug in 0. So minus negative 0 squared, that's just 0. And then plus 5 times 0, well, that's just 0. So we don't have to worry about that too much. Plus, now plug in 5, so you get 25. And I'm on the second part here. So I got 25 minus 5 times 5 is 25 minus, now I have to put in 5 halves. So 25 fourths minus 25 halves. This stuff will go away. This stuff is just 0. And it looks like I have 2 of the 25 fourths. So it's going to be negative 50 fourths. And then I'll have 2 of the 25 halves. So plus 50 halves. And then find a common denominator. Negative 50 over 4 plus 100 over 4 is going to be 50 over 4. And then you can simplify that to 25 halves. Okay. Next section, then what we got here? 5.5 was all about U substitutions, probably the most important method you learn in Calc 1 with regards to integration. So 9 to 27 odd, 35 to 53 odd, and then 65 to 83 odd. So looking at number 17 first, or well, I forgot, we don't have numbers now, just example. Integral of x all over 1 minus x squared cubed. So the deal with the u sub, you want to kind of make it into a simpler integral. Okay, and it's kind of like the reverse of a chain rule. So you're looking for the function itself and then the derivative of it, of the guts. So the function itself would be like this guy, and then this thing up top is kind of like its derivative, more or less. It's off by a constant. So that's why I do this u work over here. So I let u equal 1 minus x squared, and then my differential, derivative 1 is 0, derivative of negative x squared is negative 2x dx. So if you solve for dx, you'll note there's a negative 1/2 floating about, and we'll be able to get rid of that chain rule result in the numerator. So anyways, going here, do our substitutions. So u cubed now on the bottom. Then negative du all over 2x for dx. We can factor out a negative 1/2. We get our x's to cancel, which we need to happen to go forward. And then we're left with this elementary integral, u cubed, u to the negative 3, now du. So 1 over u cubed is u to the negative 3. Okay, negative 1/2 then, u to the negative 3 plus 1 is negative 2, and then divided by negative 2, or multiplied by negative 1/2 if you'd rather. Don't forget your integration constant. Okay. Then negative 1/2 times negative 1/2 give you 1/4. Taking the u to the negative 2 and plopping that into the denominator for u squared. And then back sub, if you begin in x, you must end in x. And then plus c. Okay. And it's kind of that same game for the most part. Every once in a while they'll throw a bit of a curveball at you, and I'll do one of those here in a second. Okay, but let's look at this next example. Here's a trig example. Sine 2x cosine 2x dx. You can use identities sometimes to simplify these, depending on how familiar you are with the identities. I'm not all that familiar, so I just do a u sub. I'm going to let u equal sine of 2x, and then du will equal the derivative of that, right? So it's cosine 2x times the derivative of 2x, which is just 2 dx. And then my dx will be du all over 2 cosine 2x. So I can always like to box off my work and keep everything really nice and separate. Here I have the integral then of u times the cosine of 2x times dx, which is now du all over 2 cosine of 2x. And you'll see a nice cancellation there between the cosine 2x's. There is a factor of 1/2 that can be factored out of the integral. You're left with u du. Then I have 1/2 integral of u is u squared over 2. Let's see. And again, if you begin in x, you must end in x. So let's rewrite it as 1/4 sine of 2x squared plus c. Let's do one now that has exponential integral of e to the 7x dx. So the answer is not e to the 7x, right? It's no. You're going to have 1/7 e to the 7x. It's like the reverse of the chain rule. Instead of multiplying by 7, you divide by 7. Okay. So anyways, you could do it with a u sub. U is 7x. du is 7 dx. And then, of course, dx is du over 7. Excuse me, let's box that off. And we'll have the integral of e to the u times dx, which is du over 7. So I factor out the 1/7, and I just have an elementary integral, e to the u du. And of course I can integrate that. We're just going to e to the u. And if you begin in x, you must end in x. So I back substitute, and there it is, just as predicted. Okay. Okay, this next one is one of those tricky ones where the u sub doesn't quite work. It kind of works, but not quite, right? And always make sure I put something like this on my test. But anyways, you try u equals x plus 6, and then the du is just the dx, right? Or if you'd rather, dx is equal to du or whatever. Okay, so if you try the do your sub, you're still going to have that pesky x hanging out, living off living off the land, I guess. I don't know. So anyways, what do? Well, you go back to this original formula and solve for x. So x is actually u minus 6. Let's box off that work. And then we can rewrite it in terms of u's. And then u to the 1/2, of course. So then you have to distribute this to make it integrable. So u to the 1 plus 1/2 is 3/2 minus 6u to the 1/2. And then we need to integrate that with respect to u. So I'll have u to the 3/2 plus 2/2 is u to the 5/2 times the reciprocal, minus 6u now to the 3/2 times 2/3, and then plus c. And then we could back substitute, yeah. So 2/5, we have x plus 6 to the 5/2. 3 goes in the 6 2 times, so we get minus 4 times x plus 6 to the 3/2, and then plus c. I always put 1 like that on the test, but okay. Let's do some ones when we evaluate. So there were 2 methods of evaluation I gave you in the lecture notes. You can immediately change the bounds once you do your u sub. Not bounds, but they call them limits. On the integral itself. So this thing and this thing need to be changed, or you could wait till the end and just do a back sub. Okay. So let me do one of each type. So here, again, u is x cubed plus 1, and then du will be 3x squared dx, and then of course dx is du over 3x squared. So I'll end up with the integral of 2x squared times the square root of u, which is u to the 1/2, times dx, which is du over 3x squared. And then I got some nice cancellations, constant of 2/3, and then u to the 1/2 du. And I'm going to go ahead and change my limits on my integral. Okay, so you have to go u of, what's the upper guy, 2? And then u of 1, and you just use this formula that you created for your u sub to evaluate those. So u of 2, you're plugging in 2 for x, so you get 2 cubed, which is 8, plus 1 is 9, and then 1 cubed is 1, plus 1 is 2. So you're now integrating from 2 to 9, and you could kind of forget about the x stuff now. So you'll end up with 2/3, u to the 1/2 plus 1 is 3/2 times 2/3, and we evaluate from 2 to 9, and then that'll be 4/9, and we're plugging in 9 first, so 9 to the 3/2, and then plug in 2 to the 3/2. I'm going to have to use a calculator to evaluate that. Most likely, if they want an exact answer, 9 to the 3/2 is the same as 9 to the 1/2 cubed, and that's 2 cubed. Okay, so 2 cubed is 8. Minus 2 to the 3/2. Okay, so that's the square root of 2 cubed. Okay, and what is that? Well, that's square root 2 times square root 2 times square root 2, which is really just 2 square root 2. Okay, so that guy is minus 2 square root 2, and that would be an answer which didn't have any approximation issues to worry about. So I guess that would kind of do it. Wait a second. It's 3. Oh, I'm totally sorry. 9 to the 1/2 is square root of 9 is 3. I'm sorry. And then 3 cubed is 27. So it's not 8. It's 27. Sorry about that. Okay, so that's the exact answer. If that's what they want, you can get that. Okay, so that's the first method. You immediately kind of change the limits on the integral into terms of u, and then you can kind of forget about the u material. Let's look at the sort of do a different version then on this next example. I don't care which method you use, just so long as you don't screw it up. So anyways, here dx over square root of 2x plus 1. Okay, so in this example, what I'll do is just totally drop the limits into the end and I'll back sub. Okay, so u in this case, I'm going with the 2x plus 1. du will be 2 dx, so we have this 1/2 constant floating about. Okay, so I'm just going to drop the limits on the integral, not even write them, and I have 1 all over the square root of u times dx, which is now 1/2 du. We could factor out the 1/2, and we're going to use the power rule, so let's rewrite 1 over square root of u as u to the negative 1/2 du. And then you have 1/2 u to the negative 1/2 plus 1 is u to the positive 1/2, and then multiplied by the reciprocal. And I have to remind myself to evaluate. 1/2 times 2 is just 1. Okay, and then I have to back sub. So I have 2x plus 1 to the 1/2. And now I could rewrite my limits in, because I know what they are in terms of x. And then I evaluate. So plug in 4, I'll have 9 to the 1/2, minus plug in 0, I'll have 1 to the 1/2. 9 to the 1/2 is 3, got it right this time. And then 3 minus 1 is 2, so our answer is 2. Okay, so again, I don't care which method you use, so long as you do it correctly, I'll be happy. Okay. 5.7 now. We're looking at exercises similar to 5 to 41 odd, 51 to 57 odd, and this is basically the natural log integral. Okay, so the integral of 1 over u du is ln absolute value of u plus c. Right? Okay, so let's try it. First example. The integral of x all over x squared minus 3 dx. Okay, so u sub on the x squared minus 3. So du will be 2x dx, and then dx will be du over 2x. So our integral will become integral of x over u times du over 2x. Nice cancellation amongst the x's. You could factor out a 1/2 constant, and you're left with the integral of 1 over u du, which is the natural log integral. So you get 1/2 ln absolute value of u plus c, and then you back sub. Don't forget your absolute values, x squared minus 3, c. Let's keep on going. Integral of x squared minus 4 over x dx. So in this case, you're going to want to butterfly it. So you have the integral of x squared over x, which is just x, minus 4 over x dx. Okay, and then the first part of the integral, the x, that's just x squared over 2. Then minus 4. The integral of 1 over x will be ln of the absolute value of x and plus c. Let's look at another one. So do you remember how to do long division? Is kind of the caption underneath this question. And that's what I have to do in order to get it done. So you're going to go x minus 3 into x cubed minus 3x squared plus 0x, if you like doing placeholders, plus 5. And then we're going to divide. So what times x is x cubed? That would be x squared. So you get x cubed minus 3x squared. And subtract these. You get 0. And then, yeah, 0. And then you can bring down the next term, which is just 0. And then 5. Okay, it's just remainder 5. And that's it. So you'll have the integral of x squared plus 5 all over x minus 3 dx. And we can integrate that, no problem. So the first guy is x cubed over 3. And then plus, you can factor out a 5, and up to the integral of 1 over x minus 3 dx. You can integrate, that's just the 5 ln of absolute value x minus 3. But if you want to do a u sub, be careful, by all means. Du will just be dx. Okay, so we'll end up with x cubed over 3 plus 5 integral of 1 over u times dx is du. Okay, so that would be x cubed over 3 plus 5 ln absolute value of u plus c. And then back sub and you're done. So x cubed over 3 plus 5 ln absolute value of x minus 3 plus c. Okay. Of course, we can now do weird tangent ones. So let's look at one of those. Integral of tan of 5 theta d theta. Okay. So this is one I advise you to have memorized. You may have had one or two formulas. The negative ln of the absolute value of cosine of 5 theta plus c, and of course it'll be over 5 at the end of the day. Or you can have ln of the absolute value of secant of 5 theta all over 5 plus c. If you forget the formulas, and if you're not, I sort of did it without a u sub, never fear, you can always just translate it into tan. Tan of 5 theta is really the same thing as sine of 5 theta all over cosine 5 theta. And then you could do a u sub, right? So you could say, oh, hey, let's let u equal cosine of 5 theta. And then du will be negative sine of 5 theta times 5. So it's negative 5 sine theta d theta. And then this will be, d theta will be du negative all over 5 sine 5 theta. That's where that 1/5 is coming from. So we can rewrite this as the integral of sine of 5 theta all over u times negative du all over 5 sine of 5 theta. And the sine 5 thetas magically disappear. And you could pull out a factor of negative 1/5. And then you just have your natural log integral. So we'll end up with negative 1/5 ln of the absolute value of u plus c. And then if you back sub, that will just be negative 1/5 ln absolute value of cosine of 5 theta plus c, which is what I got above. Just sort of guessing my way through it. Okay. Let's move on to 5.8. So 5.8, we had 2 basic formulas we need to memorize there. This is 3 to the 45 odd. You may need to make some flashcards. I've sort of suggested you do that previous lectures. So the formulas we need, in particular though, du all over the square root of a squared minus u squared. That is our arc sine, or sine inverse if you'd rather. Sine inverse of u over a plus c. And the other one, du all over a squared plus u squared, no square root, indicates it's an arc tan. So it would be 1 all over a tan inverse of u all over a plus c. Okay, well, let's take a look at some of these. So example, t all over the square root of 1 minus t to the fourth dt. Doesn't quite look like an inverse sign, but it is. Basically, you're going to have to do a u sub for t squared, because 1 minus t to the fourth is the same as 1 minus t squared squared. Okay, so let u equal t squared, and things will work out. Du is 2t dt. And dt is du all over 2t. So we can bounce this off and rewrite our integral. So I have t all over the square root of 1 minus u squared times dt, which is now du over 2t. And we have a nice cancellation of the t's. There's a factor of 1/2, which can be pulled out. And you're left with the formula for arc sine, where the a value is just 1. Okay? So the a is 1 in our formula, and we have 1/2, can't forget about that, sine inverse of u all over 1 plus c, and then back subbing 1/2 sine inverse t squared over 1, which is just t squared, and then plus c. Okay. I'll only ask you for inverse sines or inverse tans, so those are the only formulas you'll need for this section. Let's look at a tan version. So this example is a tan type. Integral of t, and it's kind of the same idea, all over t to the fourth plus 25 dt. So again, I'm just going to let my u be the t squared, because t to the fourth is the same as t squared squared. So u is t squared, and then du will be 2t dt, and then dt will be du all over 2t. Okay, so I'll have the integral of t all over u squared plus 25 times dt, which is du over 2t. Get a nice cancellation of the t's. Goodbye, goodbye. There's a factor of 1/2 I can pull out. We'll have 1/2 integral du all over u squared plus 25, which is an inverse tan, such that the a value in this case is 5. Okay, so a is 5. In the formula, that'll give me 1 all over 5 times tan inverse of u all over 5 plus c. And then you back sub and you're done. Okay, so this will be 1 over 5 tan inverse of t squared over 5 plus c. Okay. The last section then is on hyperbolics, 5.9, looking at problems like 25 to 33 odd, and then 45 to 59 odd. Basically, you just have to know how to differentiate them and how to integrate them. I'm not putting any of the weird inverse hyperbolics on there. No, all that stuff, no. Okay, so first, just finding the derivative of these characters. Example, y equals the natural log of sinh x. So if you know the trig derivatives, you kind of almost know the hyperbolic derivatives. They're just the same, except the negatives are kind of wishy-washy, right? So anyways, the derivative of this guy, y prime, is going to be 1 all over the guts times the derivative of the guts. That's the chain rule, x. And of course, if you're ambitious enough, you can rewrite it as Koth, if you know the identities well enough. But this answer would be fine for me. I would be happy with that. Let's look at another one. So we have h of x equals 1/4 sinh of 2x minus x over 2. Okay. Whoops, gotta carry away with my 1/4. It's just floating out there in the middle of nowhere. Okay, so h prime of x, what do we have? 1/4. This should be sinh, not sin. Derivative of sinh is cosh. 2x, and then the chain rule, the derivative of 2x is 2, minus derivative of x over 2 is just 1/2. Clean it up a bit. 2 times 1/4 is 1/2. Oh, and then we also have, oh jeez, the 2x. So 2x times 2 times 1/4 is going to be just x. 2x times 2 times 1/4 will be 4x times 1/4, which will be just x. Okay. X cosh. Whoops, the 2x was inside the cosh. Oh, let's try that again. What else is bothering me? This does not look like a cosh. Looks like something weird. Okay, so it's just 1/4 times 2 will give you the 1/2, and then cosh 2x minus 1/2. There it is. Okay. You also have to know how to integrate these little characters. And what do we have? Integral of sinh 1 minus 2x dx. And in this case, we need a u sub, no doubt. So it's 1 minus 2x. du is negative 2 dx. So there's a negative 1/2 floating about. Negative du over 2. So this will be the integral of sinh of u times negative du over 2. Factor out the negative 1/2. So you get negative 1/2 integral of sinh of u du. So that's going to be negative 1/2. The integral of sinh is cosh of u plus c. And then finally back sub. Negative 1/2 cosh of 1 minus 2x plus c. Okay, let's do one more, and then we'll call it quits. Integral of cosh x over sinh x dx. Okay, this guy is just the integral of coth, right? And we could figure that integral then by using a u sub on sinh. So du will be cosh of x dx. And of course dx will be du all over cosh of x. And then we do our substitutions here. And we get cosh of x over u times dx, which is now du all over the cosh of x. And then we remove factors, and we end up with the integral of du over u. So that's just our natural log integral. So we end up with the ln of the absolute value of u plus c, and then of course back sub. Okay. And that will finish us off for the day. So do what you got to do to get those formulas memorized. Make note cards, whatever gets the job done. And okay, I guess that's about it. And we'll, thank you for watching, and we'll see you next time.